Bam! Mr. Tarrou. In this second of two videos I'm doing with optimization problems in calculus, we're going to do three examples dealing with volume. We're going to minimize the volume of a rectangular solid, a box, with a fixed surface area. We are going to find the maximum volume of a cone that we can inscribe inside of a sphere. And then we are going to minimize the cost of creating or manufacturing one of those sort of like natural, you see these type of tanks for holding natural gas where it's a cylinder in the middle and then there's two hemispheres on the sides, kind of like a gigantic pill-shaped tank. We're going to do a problem where we minimize the construction costs of one of those tanks based on some parameters. And to do that, we're going to walk these 5 steps, hopefully the same 5 steps you saw me introduce in my previous video where we did some maximization and minimization problems dealing with length. So we're going to identify all the variables of interest, what are you given, and what do you need to solve for. And again, just like in the previous video, draw yourself a picture so you understand what these numbers represent and what a reasonable domain is. We're going to set up a primary equation based on what you want to maximize or minimize. We're going to again set up a second equation based on some fixed value, and we're going to use that equation to rewrite the primary equation in terms of only one variable so that we can then apply find the derivative of it and then find some critical values, and then ultimately, of course, our goal is to solve for those values that will either maximize or minimize, whatever the variable of interest is that the question asks for. So, we have a lot of work to do. Let's get to it. Determine the dimensions of a rectangular solid with a square base and with a maximum volume if the surface area is 278 square centimeters. Now I have a good idea that this is probably going to be similar to the first example of my previous video where we had a fixed perimeter and we wanted to maximize the area of a rectangle. That ended up being a square, so I have a pretty good idea that the most efficient way of holding a maximum volume when we have a fixed surface area of 278, the most efficient rectangular solid is probably going to be a square. But this is the first example dealing with volume, so let's let the calculus verify that and see if we're right when we're done. And then we'll have a couple of examples, of course, that we can't just glance at and do, or hypothesize even what maybe the answer would be before we start the problem. Okay, so we're supposed to have a fixed surface area of 278. Okay, so we're going to need a formula about surface area, and the surface area of this rectangular solid, well, we have two bases which have a length and which are the same, so we have 2x squared. We've got a front plane here or rectangle of width of x and height of y, and of course there's going to be 4 of those because we do have a square base, so there's 4, 1, 2, 3, and then the back side is 4 xy. And that fixed surface area is supposed to be, of course, again, 278 square centimeters. So we have 2x squared plus 4xy is equal to 278. Okay. Now, that's going to be our secondary equation because it's based off of a fixed value. And it's not what we're trying to maximize or minimize. Okay, we're trying to maximize volume. So the volume of a rectangular solid is equal to the area of any rectangular solid, and much like a cylinder, is just the area of the base times the height. So the base is going to be x times x, which is x squared, times the height, which is y. Okay, now again, we need to take our secondary equation and allow us to write the primary equation in terms of only one variable so we can work with the derivative process and try and find the max or minimum by minimize it. And we can solve for any variable that we like as long as we, well, not as long as, you can solve again whatever you want. We can put this v in terms of x or in terms of y. Just pick the one that's going to be the most efficient. And if I look at this, it's going to be, quite a bit of work to try and get this equation solved for x, so I think it's going to be a little bit easier to get y in terms of x and do that substitution up here. So let's speed this up a little bit. Voila! I've taken my equation here, solved it for y, and did a little bit of reducing. This y is equal to, therefore, 139 minus x squared over 2x, and put that back into my volume formula, my primary function, which I'm going to maximize, and wrote it in terms of x. Now we're going to have to find the first derivative of this function so that, we can do the first derivative test to find either relative max or mins. I can do the second derivative test as well if I like. We also need to look at a reasonable domain. Now x, the length of the sides of the base, can shrink to be almost zero, so we have a very, very, very tall, skinny rectangular solid or box, and I don't think that's going to be very efficient for holding volume. Or I can take these sides and let them extend out until the two bases, basically take up, what's effectively all of the surface area. So I'm going to, again, pause. We're going to simplify this a little bit. And that reasonable domain for x is going to be from 0. And then what I'm going to do is, again, this idea of letting the bases expand until it takes up basically all of the surface area, which again I don't think is going to be a maximum for the volume, but just to discuss this reasonable domain, we're going to set let's see what here. We got a bottom and a top, so we have 2x squared. We're going to set that equal to 278 and find out just how big can x get for this reasonable domain. So as you saw, we found an approximate solution for x that it can approach approximately 11.79, so this is our reasonable domain. I took the x squared times the 2x in the denominator, or actually dividing by 2x, excuse me, and that cancels or reduces a little bit. I took that 1x that was left, distributed it through the parentheses. We have 139x minus x cubed. And again, just to clean this up a little bit more, to more easily apply the first derivative or find the first derivative, I took that and split it up separately. We have 139 over 2x minus 1/2 x cubed. So that means that we now have our volume in terms of x. We have it in a nice form to find the first derivative, and that first derivative is going to be 139 over 2 times x is going to be 139 over 2 minus, bring that 3 down, 3 times 1/2 is 3/2 x squared. Okay, so we need to find our critical values for the first derivative, and that's going to be where is it equal to 0 and where is it undefined. So what's going to make the first derivative equal to 0? Well, that's going to be 139 over 2 minus 3 over 2 x squared equals 0. And then where is that first derivative going to be undefined? Well, our first derivative doesn't have any way of possibly being undefined, so this is going to have no solution. Let's get this up here. So doing a little bit of algebra, we have a critical value of 6.807. Now, is this a relative max or min? Now I can apply the first derivative test by setting up some intervals between 0 and 6.8, and then from 6.8 approximately to 11.79, and do the first derivative test to see if this is a relative max or min. Or I can go to the second derivative test, which for this one is actually going to be pretty simple. I'm going to take this first derivative and find the derivative again. So the second derivative is equal to, well, let's see here, 139 over 2 is going to be 0, and negative 3/2 times 2 is going to be negative 3. And reduce that exponent by 1, and we just simply have negative 3x. Okay, so where my first derivative is equal to 0. If my second derivative is positive, it's concave up, and that means this is a relative minimum. Hope not, because we're trying to maximize the volume. Or if the second derivative is negative, where the first derivative is equal to 0, then we have a concave down situation, and that's a relative max. And of course, if the second derivative comes up to a value of 0, then it's not really telling us anything. We'll have to revert back to the first derivative test. However, we can see that the second derivative is x times negative 3, or x solution of x is equal to 6.08, or 6.8, excuse me. I did apply my own square root, but of course we are doing a geometry problem, and we're not going to have a negative length. So we do have just the x of positive 6.807 times negative 3 means the second derivative is a negative value, which means we are talking about a concave down situation, and this is a relative max. Okay, so what were we trying to find? Determine the dimensions. If I want to find I don't really need to test here, I don't believe. You know, when you find your relative max or mins, whatever is appropriate for the problem, and you want to test whether it is the absolute max or min, you know, you should be testing the endpoints of your domain and your critical values, all your critical values if you have more than one. But this is an open interval, and we wouldn't even, so it wouldn't be appropriate to take the value of 0 and plug it into the volume, or the 11.79, you know, because this is an open interval and you can't find max or mins, whether they're absolute or relative on an open interval, because you're just getting infinitely close to these values. And if x was 0, I wouldn't even have a solid, right? So this is it. And if I want to find the maximum volume, then I can go ahead and plug it back into here and see what that solution comes out to. But we were just asked to find the dimensions. So what do we have here? Well, we had that y was equal to 139 minus x squared over 2x. And we have the approximate value for x. So let's take that, plug it into the formula, and see what it comes out to. And our initial suspicion was correct. The x value, the approximated value for x when plugged in for the equation where y is equal to relate those two together, we get a y value which was also 6.807. So it does look like that rectangular solid does need to be the shape of a cube. That's the most efficient way that a rectangular solid is going to be able to hold volume. Now let's take a look at some questions that maybe we couldn't just have thought of at the very beginning. Find the volume of the largest right cone that can be inscribed in a sphere of radius 10. Okay, so we want to maximize the volume of a cone. Well, our primary equation is going to be volume of a cone is 1/3 pi r squared times the height. Great. Okay, so obviously we're going to have to use the fact that the sphere has a radius of 10. So let's go here, put a circle in here, or excuse me, mark off the center and identify the radius right there of 10. Okay? So we need to obviously write the volume of this cone in terms of only one variable, and it's going to be a little bit more difficult this time to come up with a secondary equation that's going to allow us to do so. So, you know, the radius of the sphere is not necessarily going to be the radius of the cone. The radius of the cone is actually this length right here. Okay, well, that's x, and that's going to change as this cone. I mean, I can take the base of this cone and move it through the sphere, and that's going to take the base of the cone and, of course, make it variable. So while the radius is 10, I'm not using that fixed value, you know, necessarily not going to take that 10 and plug it in there for the r, because it's not the same. All right. Well, how tall is it? Now the base of the cone is variable. How tall is the cone? Well, the cone obviously has, you know, this height here, and that height is going to be along, no, part of that height from this point where the top of the cone is touching or inscribed on the circle from here to here. That distance is equal to 10, and what we need to figure out is the rest of that length. And you can see I'm starting to make a little right triangle. So if I pull that right triangle out, it has a hypotenuse of 10 from the radius of the sphere. It has a length down here of x and a length up here of y. Now you might be thinking, okay, usually when I have one side of a right triangle, I want to use some kind of trig function, and you could mark off some theta in here and start working with SOHCAHTOA, but these are just lengths, and I don't think we need to take a measurement of an angle and bring it into that and incorporate trig functions. Probably a difficult method of doing this problem. No, what we normally deal with when we talk about right triangles is either those, you know, little right triangle trig formulas, SOHCAHTOA type stuff, sine, cosine, and tangent, and secant, cosecant, all other stuff, but also Pythagorean theorem. So I can say that x squared plus y squared is equal to 10 squared. Okay, so I can come up here and I can go, all right, let's see. We've got 1/3 pi r squared times h. I can write that as 1/3 pi. Okay, let's see here. We've got x squared, right? Because this isn't really the r, this is not the radius of the sphere, it's the base of this right cone. So that's going to be, r squared is going to be x squared in my diagram here, x squared. And then the height is equal to, well, the height of the cone is 10 plus h. Okay, excuse me, not h, but y, right there, because this right triangle is right there. Okay, so now I can write this in terms of either x or either y. Now, if I want to write this in terms of, like if I want to take the y out and write this function in terms of x, then I would have to say that y is equal to the square root of 100 minus x squared, and I don't want to bring radicals in there. That's going to make the derivative process more complicated. So what I'm going to do instead is I'm going to write my volume function in terms of y, because x squared is simply 100 minus y squared. Okay, so now I have my volume in terms of y, or at least it will be, which is going to be equal to 1/3 pi. The x squared is coming out, and 100 minus y squared is going in its place. Plus 10 times y. Now, I can distribute this together if I want, but I really don't think it's going to make the first, finding the first derivative process any simpler. So I'm going to actually just speed this again up a little bit and reveal that process of finding the first derivative. I'm going to take the 1/3 pi and hold it out front and work through the product rule to find the first derivative. So if you want to pause the video and practice your first derivative skills, or yeah, go ahead and do that. All right, so we applied the power rule, the product rule, of course, excuse me. We have first times the derivative of the second here, plus the second times the derivative of the first. And keeping with the idea that I want to, of course, find critical values by setting the first derivative equal to 0 and undefined, I didn't just take this negative 2y and distribute it through the parentheses, and maybe it wouldn't have been a big hassle if I had, but I noticed that we had a difference of squares here. Plus I have a 10 plus y. So if I factor that difference of squares, we get 10 plus y times 10 minus y. We have a common factor of 10 plus y. We go ahead and factor that out. And this simplifies down to the first derivative is equal to 1/3 pi times 10 plus y times 10 minus 3y. Okay, now we need to find some critical values. Where's the first derivative equal to 0 and undefined, like we said? But what is your reasonable domain? Don't forget to check that. So my reasonable domain, well, if you think of y as being just the side of a right triangle, then your reasonable domain for y is going to be right here from 0 to, actually it could be 0, to 10. Where if the height of this right triangle is 0, then you're basically right on the great circle or the equator of this hemisphere, and your right cone will be right there. Now, and then that triangle then could open up and giving you a height all the way up to 10, which is just going to be a really, really tall, skinny triangle. I don't think the volume of that's going to be very, very great, of course, or a maximum. Well, you can also think of this as being on an xy axis and incorporate this idea of coordinates, because really y is helping to determine, of course, the height of the cone. And that being said, if y starts off at being 0, the cone already has a height of 10. So really, the domain for y, as it's helping to set up the height of the cone, is between -10 and +10, because the y if you allow this to go in the opposite direction, could maybe y be -9? Well, if y is -9, then the height of the cone is 10 minus 9, which is equal to 1. So we could just be inscribing a cone that has its top up here and the height of the cone is only 1, and have a pretty shallow and probably not a whole lot of volume in a cone, cone that's inscribed in the sphere way up there. So I'm going to use that as my reasonable domain. Now, what's going to make the first derivative equal to 0? Well, v prime equal to 0, we have a function. I can just leave that 1/3 pi out there because really if either one of these factors are equal to 0, then we have a first derivative which is equal to 0. So we have 10 plus y times 10 minus 3y is equal to 0. We're going to set each of these factors equal to 0. We have 10 plus y is equal to 0, and that means that y can go down to -10. Or we have 10 minus 3y is equal to 0. That means -3y is equal to -10, and ultimately y is equal to 10 over 3. Now, are we looking at, with that critical value of y equaling 10/3, are we looking at a relative max or min? Oh, by the way, there is no values, or no solution, excuse me. Why am I keep writing y? There is no solution to the first derivative being undefined. So I don't really want to find the second derivative of this going through the product rule, so we can set up our intervals between 0 and, or excuse me, -10 to our critical value of 10/3, and then from 10/3 up to 10. And look at the values of our first derivative, f prime, or actually v prime for this problem, and see what we can find. Well, if I take a value of, say, 0, okay? If I take 0 and I do plug that in there, then I have 10 plus 0, which is 10. We have 10 minus 0, which is also going to be 10, or positive. That's really all I care about, is it being positive. And if I do that, I'm going to have a positive value times a positive value, so my first derivative in this first test interval is going to be positive. Now if I plug in a value that is larger than 10/3, or between 10/3 and 10, like 5, we have 10 plus 5, which is 15, and we have 10 minus 3 times 5, or 10 minus 15, which is a negative value. So positive times a negative, and then times positive again, means my first derivative is going to be negative in this interval, and thus we have a relative max at 10/3 f of 10/3. And I'm kind of running out of room. I think for this one, even though I wasn't asked for it, I'd like to kind of just show what that maximum volume of that cone is going to be before we finish up the problem. And, oh, never mind. We are finding the volume. But I am out of space, so let me get this cleaned up a little bit, and we'll find that maximum volume of our right cone that's inscribed in our sphere. So we got this all cleaned up. I took that 10/3, plugged it into that we found for y, and took that value and plugged it into our volume in terms of y, and got 32,000 pi over 8, or approximately 1,241.12 cubic units, which is our maximum volume of the cone. Now, if your reasonable domain was set up for y to be between 0 and up to 10, you could test that one, and you would test that that closed value of 0. You would have a volume of 1047.3 approximately. Of course, this is greater, so this is our maximum volume of this cone inscribed in a sphere with a radius of 10. And by the way, if you wanted to know the radius of your cone, of course, that would be x, and x would be equal to the square root of 100 minus y, which was 10/3 squared. And just right off the top of my head, it comes out to be 20 square roots of 2 over 3. I got one more example, and it's going to be kind of a long one. Thanks for watching. A natural gas tank must have the volume of 5,500 cubic feet. The hemispherical ends cost 4 times as much as the cylindrical side. Find the dimensions to minimize the cost of the tank to produce it. So our secondary equation is going to be clearly based off of volume because it is fixed. So the volume of this combination of cylinder and sphere is going to be 5,500 is equal to, that's annoying, the volume of the cylinder. Volume of a cylinder, or right cylinder anyway, is actually all of them. Area of the base times the height, so pi r squared times the height. And then to that we need to add the volume of a sphere. Well, the volume of a sphere is 4/3 pi r cubed. Okay. Now before we even look, well, that would be a bad idea. I mean, I was going to say before we even look at the function for the cost, I'm pretty sure I'm going to try and get this equation solved for h because, man, I don't want to solve for r with the square and the cube terms. Actually, let's go ahead and just pause the video and get that done because I know we're going to need that for the cost function. I'm going to just take this and of course solve it for h by subtracting both sides by 4/3 pi r cubed and then dividing by pi r squared. So we have h in terms of r. We'll see how we need to use that substitution in our cost function. Well, our cost function. Now, the tank is measured or being maintained at 5,500 cubic square feet. So let's just assume that the material for the outside is being sold just for conversational purposes as square feet. The metal is around the outside, so it's basically representing the surface area of this tank holding the volume inside, which is the natural gas. So we're talking about surface area. If we take the center of this tank out and we just allow the two hemispherical ends to come together, we're talking about the surface area of a sphere. Now the surface area of a sphere is going to be 4 pi r squared. Now that's going to be the surface area square feet, how they're selling the material just for conversational purposes, and that cost is 4 times as much. Now how much is it cost per square foot? I don't know, but I'm going to allow K to be the price per square foot, and the ends, the hemispherical ends, are costing 4 times as much as, again, that cylindrical side. So this is going to be the cost of the end caps plus the sides. Okay, well, if I take these off and I cut this and I open this up, then we basically are just finding the area of a rectangle. That sheet of metal is having to wrap around the tank. In other words, its length, if you will, is the same distance as the circumference of that circle. So we're looking at 2 pi r, and then the height, right? So now how much is that number of square feet of material costing? I don't know, but it's going to be that constant of K. Now both of these terms, just to clean this up a little bit, both of these terms have a factor of 2 and a factor of K. They both have a pi as well, and you could factor that out, but when I go ahead and do the substitution in for h, I'm going to introduce more pi's, so I'm just going to let them cancel as I introduce that if they happen to, and I'm just going to bring out that 2K. So 2K, parentheses, I'm actually reshooting this part of the scene because I was talking too much and forgot to add those in and made some other kind of silly mistake. We have 4 times 4, which is 16, divided by 2, which is 8, and the K is out. So we have 8 pi r squared, we'll close that up, plus 2 divided by 2 is 1. We brought the K out, so we're just left with pi r h. And you can wrap that in parentheses too if you'd like, just to really emphasize those two terms. Don't really need that there, to be honest. Now, we've got a cost function in terms of, well, the K is a constant, in terms of R and H. Okay, so now we can take our secondary function, which is relating the H and R together, again, based on the volume, and do a nice substitution. We have the cost in terms of R is equal to 2K times 8 pi r squared plus pi r h. it's really better to use too many parentheses than not enough and forget that you have to do some kind of distributive process somewhere. So this is a little bit of overkill, but that's okay. The h, which I just unintentionally wrote, is equal to 5,500 times pi r squared. I just say times divided by pi r squared minus 4/3 r. You can see why sometimes it's better for me to pause the video and write this instead of writing and thinking and talking at the same time. Okay, this is going to need a little bit of cleanup before we try and find the first derivative, and for that I am going to pause and make sure I don't make some small mistake as I'm talking. Alright, so I took my pi r and I distributed it through the parentheses, and the pi's are going to cancel here with the denominator, and that one r is going to cancel with one of those two r's, leaving us with 5,500 over r, and then minus 4/3, and there's nothing left to cancel, so we just have 4/3 pi r squared. Now we have a pi r squared, so we have a couple of like terms, and 8 over 1 minus 4 over 3, of course you need to calm the denominator, so 8 over 1 becomes 24 over 3 when you multiply the numerator and denominator by 3, and 24 minus 4 is equal to 20 over 3 pi r squared plus 5,500 over r. Okay, reasonable domain. Well, now that I've got my function just in terms of r, my radius of my tank can approach 0, which isn't going to be really very efficient for holding natural gas, but I can also let this r value and just increase, and then of course as this r value increases, the height of the tank is going to be allowed to reduce to keep that fixed volume of 5,500 cubic feet until eventually really you could just let the radius expand until the height is 0. So the maximum measure for the radius is found by doing the volume that we must hold times the volume of our sphere, which is 4/3. Well, it might be a sphere if we don't need it, if we need a height of 0 to create the tank and minimize the cost. But for that sphere, it's 4/3 pi r cubed. We plug in that 5,500, divide both sides by 4/3 pi, and cube root both sides, and we get an approximated value of 10.9503 for the largest that our radius can get. So when we get done with the problem, we want to test that value to make sure that it is not a minimized cost for the tank. Okay, but getting all that, we need to find the first derivative, so that is going to be c prime of r, or the first derivative of r, is going to be equal to 2k times the derivative of the inside function here. We've got 2 times 20, which is going to be 40 over 3, pi r. And now if I let this r float up, I can use the quotient rule as the quotient property as well, or rule for finding derivatives. But if I let the r float up and get 5,500 times r to the negative 1, we take that negative 1, drop it down, we have minus 5,500. That r to the negative 1 is up there, we drop that exponent down, we reduce it by 1, negative 1 minus 1 is negative 2, and so we end up with negative 5,500 over r squared. Now, what is going to make this first derivative equal to 0 or undefined for our critical values? Well, I need to clean up my board here so I have some room to do this work. So let's get this right now. Or now. So we got this cleaned up. We want to find out where the first derivative, of course, again, is equal to 0 or undefined for our critical values. And the first derivative is going to be undefined. Well, I do have a division where the variable is in the denominator, and I can't divide by 0. So it's undefined at an r value of 0, but we've already discussed that that's not in our reasonable domain, so I don't need to worry about that value. Where is it equal to 0? Okay, well, our first derivative is equal to 0, where of course I take this function and set it equal to 0. We have let's see here, 40 over 3 pi r minus 5,500 over r squared is equal to 0. We can multiply both sides by r just to get it out of the denominator, or r squared, excuse me, if you like. That is going to come out to be 40 pi r cubed minus 5,500, over 3, minus 5,500 is equal to 0. We're going to move that 5,500 over to the other side and get 40 pi r cubed over 3 equals 5,500. Multiply both sides by 3, and we get 40 pi r cubed. 5,000 times 3 is 15,000. 500 times 3 is 1,500, so 15,000 and 1,500 is 16,500. We're going to divide both sides by 40 pi. This reduces, but we're going to do a decimal approximation anyway, so I'm just going to write 16,500 divided by 40 pi, cube root both sides, and r comes out to be approximately, right off the top of my head, approximately 5.08. Okay, now, is this minimizing cost, okay? Actually, is it even a relative minimum? What we need to do now is drop our eraser and test our first derivative. Okay, so our first derivative here, c prime, or our intervals are going to be from 0 to 5.08, and then from 5.08 to 10.9503, and I'm just going to pretend like I can do this on the top of my head. We are going to take a value of 1 and plug it into this first derivative, really here. This is obviously a positive cost. We'll just focus on this inside function. And when we take a value of 1 and plug it into here, it's going to come out to be negative. And when you take a value from 5.08 to 10.95 and you plug it into your first derivative, it is going to come out to be a positive value, showing you that you do have a relative minimum at 5.08 f of, well, actually c for cost, right? C of 5.08. And I'm out of space again. That cost. Now, if you take this value of, actually, let's go ahead and, I don't want to verbally say it, let's just erase another part of the board and do it again. So, the cost. If you take that 5.08 and you plug it back into the cost function in terms of r, you are going to find that it comes out to be 3,246.33 times k, whatever this product is that's costing per square foot. And then the other test interval, when we let the radius expand to as much as possible, reducing the height to 0 and just having basically a sphere as our tank, that came out to be a cost of 6,027.3 K. And remember, we're not talking about the most efficient way, we're not talking about minimizing the amount of material it takes to hold this volume of 5,500 cubic feet. We're minimizing the cost, right? And these end caps cost a lot more than the cylindrical side. So we do have, when C is equal to 5.08, we do have a minimum cost value of 3246.33 K, or when the radius is 5.08 feet, which I probably should have put up there, right? Now, how tall is the tank going to be? Or at least, well, not how tall from like end to end, but how tall is the cylindrical sides, or the distance between the two hemispherical end caps, or what is h? Well, h is equal to approximately, because these are all rounded off decimals, of 5,500 divided by pi times 5.08 squared minus 4/3 times 5.08, and that gives you an h value that is approximately, right off the top of my head, equal to, making sure I wrote this all right, 61.07 feet. That's quite a long tank. Okay, so, and the radius of the end caps there is, again, a relatively small 5 feet to the actual length of the tank, which is 61. That is, of course, again, one more time, because the hemispherical end caps cost 4 times as much. So, I'm Mr. True, the end of my last example. Time for you. Go do your homework.